Tonight the moon is quietly pulling on the sea, not with a visible hand, not with waves of silver light, and not in the simple way it can sometimes look in a diagram, but through gravity. Across the planet, the ocean is rising and falling in a rhythm so familiar that it can almost seem ordinary, even though it is one of the clearest signs that Earth is not moving through space alone. At the shoreline, the tide creeps over sand, fills rock pools, lifts boats from harbour mud, and then, hours later, retreats again as if the sea has quietly changed its mind. In some places, this motion is gentle. In others, the water can climb by many meters, transforming an entire coast before slowly slipping away again. And above it all, the moon keeps moving. Hello, and welcome to the Late Lab. It's lovely to have you here. Where in the world are you watching from tonight? Maybe you're near the coast, where the tide is always arriving or leaving. Maybe you're far inland, where the ocean feels distant, but the moon still rises just the same. Wherever you are and however your day has been, you're very welcome here. If you enjoy calm, relaxing science videos like this, liking the video and subscribing to the Late Lab is always appreciated. It helps support the channel, and it lets more people find these quiet journeys through science, space, nature, and the strange little rules that hold reality together. And to those already subscribed, thank you. Your support genuinely means a lot. The sea does not look as if it is obeying something in the sky. From the edge of a quiet shore, it seems almost local, almost personal. A thin lace of water slides over the sand, pauses around a stone, fills the small hollows left by footprints, and then slowly reaches a little farther. Boats that rested on mud a few hours earlier begin to lift. Rock pools that were isolated and still are joined again to the wider ocean. The shoreline changes shape without hurry, as though the planet is breathing through water. Then, later, the motion reverses. The sea draws back. Wet sand shines in the low light. Seaweed settles against the rocks. Channels appear where there was open water, and the same beach seems larger, flatter, and newly revealed. Nothing dramatic has exploded. No great wave has arrived, and yet an enormous amount of seawater has moved, quietly and reliably, as it has done for as long as human beings have stood beside the coast and wondered what the ocean was doing. This rising and falling is called the tide, and it is one of the most visible rhythms on Earth. It can be measured with instruments, predicted in tide tables, followed by sailors, watched by harbour workers, and felt by anyone who has ever placed a towel too close to the advancing sea and then had to perform the traditional beach sprint of mild regret. At first, the explanation can sound simple. The moon pulls on the ocean and the water rises. That is not completely wrong, but it is much too small a picture. The moon does not control the ocean like a hand moving water across a table. It does not reach down and scoop the sea toward itself. Instead, the moon shapes the ocean through gravity, through distance, through orbital motion, and through the rotation of Earth beneath it. The important idea is that the moon pulls on every part of Earth. It pulls on the ocean, but it also pulls on the land, the atmosphere, and the planet's solid interior. The side of Earth facing the moon is a little closer to it, so it feels a slightly stronger lunar pull. The far side of Earth is a little farther away, so it feels a slightly weaker pull. That difference across Earth's diameter creates what scientists call a tidal force. It is not simply gravity, but the unevenness of gravity from one side of a body to another. That uneven pull gently stretches Earth and its oceans along the line between Earth and the moon. The effect is small compared with Earth's own gravity, which is why the ocean does not simply fly upward into space, thankfully avoiding a very damp and inconvenient astronomy problem. But over the scale of an entire planet, even a subtle stretching force can matter. Oceans are vast, mobile, and connected. Give them a repeated gravitational rhythm, and they respond. Still, tides are not just a neat bulge of water following the moon around the globe. The real ocean is more complicated and more interesting than that. Earth is spinning. The moon is orbiting. The sun is adding its own gravitational influence. Continents interrupt the flow of water. Ocean basins have different depths and shapes. Seafloor ridges, continental shelves, bays, estuaries, islands, and coastlines all reshape the tide before it reaches any particular shore. This is why tides are planetary rather than merely local. A person standing on a beach may see water rising against a familiar wall or retreating from a stretch of sand, but that local motion is part of a much larger system. The whole ocean is responding not only to the moon, but to the combined behavior of Earth, moon, sun, gravity, rotation, and geography. The tide at one harbour is the local expression of a global pattern. Modern tide prediction reflects this complexity. Scientific bodies such as the National Oceanic and Atmospheric Administration in the United States, the UK Hydrographic Office, and national hydrographic agencies around the world use observations, astronomy, mathematics, tide gauges, satellite measurements, and local records to predict when the sea will rise and fall. The daily tide table may look simple, but behind it is a careful understanding of celestial mechanics and ocean behaviour. So the familiar tide at the shoreline is not just water moving in and out. It is a visible clue to a much deeper relationship. A distant grey world in the sky, roughly 384,000 kilometres away on average, can help move enormous volumes of seawater because gravity does not need touch. It works across space, quietly shaping motion. The moon controls the ocean not by command but by influence. It sets a rhythm. Earth turns through that rhythm. The sun modifies it. The continents and seafloor translate it into local patterns, and from a quiet beach, all of that becomes something simple enough to watch. The sea arriving, the sea leaving, and the planet breathing beneath the moon. Long before anyone could describe gravity with mathematics, people were already learning that the sea had habits. For coastal communities, tides were not an abstract scientific puzzle. They were part of daily survival. A tide arriving at the wrong moment could trap a traveller on a sandbank, lift a boat free from mud, flood a narrow channel, or close off a path that had been open only a short while before. A tide leaving at the right moment could reveal shellfish, expose fishing grounds, uncover seaweed, or let people cross stretches of shore that would later disappear beneath water again. The ocean was not just there. It was keeping time. People who lived close to the sea learned this rhythm through careful attention. They watched where the water reached on rocks. They noticed which pools stayed full longest. They remembered when boats could enter shallow harbours, and when they would be left resting awkwardly on the seabed, looking slightly embarrassed for themselves. They learned that the sea could not be treated as a flat, permanent surface. It was a moving boundary, and anyone who ignored that boundary did not usually need a lecture. The wet shoes were lecture enough. The connection with the moon was noticed because the timing often matched the sky. The sea's rise and fall did not happen randomly. Larger tidal ranges often appeared around the new moon and full moon, when the moon and sun were roughly lined up with Earth. Smaller tidal ranges often appeared near the quarter phases, when the moon and sun were pulling from different directions. Ancient people did not need modern instruments to see that the moon's changing appearance and the ocean's changing behaviour seemed to belong to the same pattern. Across the world, different cultures built practical knowledge around this. Polynesian navigators, travelling across the Pacific with extraordinary skill, read the sea through swells, stars, winds, currents, birds, clouds, and island patterns. Tides were part of a much larger ocean literacy, learned through experience and passed through generations. In the Mediterranean, sailors and harbour communities watched local tide behaviour, even though the Mediterranean's tidal range is often smaller than that of the open Atlantic. Around the North Sea and the Atlantic coasts of Europe, where tides can be far more dramatic, coastal life depended heavily on knowing when the water would come in and when it would retreat. This kind of knowledge was not yet modern science, but it was not primitive guesswork either. It was observation, memory, comparison, and prediction. It was the beginning of pattern recognition. Before equations, there were shorelines. Before tide gauges, there were rocks, boats, mudflats, channels, and people paying very close attention because the ocean was not especially interested in offering second chances. Ancient Greek thinkers also tried to understand tides as part of a wider desire to explain nature. Aristotle wrote about many natural phenomena, including the sea, weather, animals, motion, and the heavens. He and other Greek philosophers were trying to find order in the world, even when their explanations were limited by the knowledge available at the time. Without the modern concept of universal gravitation, tides were especially difficult. The link between moon and ocean could be observed, but the invisible force connecting them could not yet be properly explained. Much later, Galileo Galilei also tried to explain tides, and his explanation was famously wrong. Galileo connected tides to the motion of Earth, arguing that the movement of the planet helped slosh the seas around. He was partly interested in tides because he believed they could support the idea that Earth moved. In that broad sense, he was trying to connect ocean behavior with planetary motion. But he did not correctly identify the moon's gravitational role. The moon, which had been waiting in the sky with the scientific equivalent of a raised eyebrow, was rather important after all. Yet wrong explanations can still matter. Galileo's tidal theory failed, but it showed that tides were being treated as a physical problem connected to the motion of Earth and the heavens. Ancient explanations, seafaring traditions, and early natural philosophy all carried pieces of the same larger story. People knew the sea had a schedule before they knew why. They saw that the moon and the ocean seemed linked before they understood tidal force. They used the pattern before they could explain the mechanism. That is how science often begins, not with a perfect answer, but with a repeated observation that refuses to go away. The tide rises, the tide falls, the moon changes, the pattern returns. For thousands of years, people stood beside the water and noticed. Modern tide theory would eventually bring gravity, orbital motion, mathematics, and ocean physics into the picture, but the first step was simpler and older, watching the sea, watching the sky, and realizing that the ocean was keeping a schedule written partly by the moon. The missing piece was gravity. For centuries, people could see that the moon and the tides were connected, but seeing a pattern is not the same as understanding the mechanism behind it. The sea rose and fell. The moon changed its position in the sky. The timing often lined up. But the actual reason a distant object could help move oceans remained hidden until the idea of gravity became much clearer. That turning point came with Isaac Newton and his theory of universal gravitation. Newton showed that gravity was not only something that pulled apples downward or held people to the ground. Gravity was a force acting between masses everywhere in the universe. Earth pulled on the moon pulled on Earth. The sun pulled on the planets. Every object with mass attracted every other object with mass, though the strength of that attraction depended on mass and distance. This was a profound shift. It meant the same kind of force that makes a dropped stone fall to the ground also helps guide the moon around Earth and Earth around the sun. The heavens and the everyday world were no longer separate realms following entirely different rules. They were part of the same physical system. A falling apple and the orbiting moon belong to the same story, which is rather impressive for an apple, even if the apple itself had very little say in the matter. When this idea is applied to tides, the first thought is usually simple. The moon pulls on Earth's ocean. That is true, but it is still not the full explanation. The key to tides is not just that the moon pulls on Earth. The key is that the moon does not pull on every part of Earth equally. The side of Earth facing the moon is slightly closer to the moon than Earth's centre is. Because it is closer, it feels a slightly stronger lunar gravitational pull. The far side of Earth is slightly farther from the moon than Earth's centre is. Because it is farther away, it feels a slightly weaker lunar gravitational pull. The difference is tiny across everyday distances, but across the full width of Earth, which is more than 12,000 kilometres, that difference becomes important. This unevenness is what creates tidal force. Tidal force is not simply a strong upward pull lifting the ocean toward the moon. It is a stretching effect caused by gravity changing from one side of Earth to the other. The moon pulls more strongly on the near side, less strongly on the far side, and somewhere in between on Earth's centre. The result is a gentle stretching of Earth and its oceans along the line connecting Earth and the moon. A useful way to picture this is to imagine a blanket being pulled more at one end than the other. The blanket does not need to be yanked violently. Even a small difference in pull across its length can stretch it slightly. Earth's oceans respond in a somewhat similar way. Though there is no physical hand tugging at the sea, and the blanket, mercifully, is not covered in crabs, the important point is the difference from one side to the other, not just the pull itself. This also helps explain why the moon can affect the ocean, even though its gravity at Earth's surface is far weaker than Earth's own gravity. Earth's gravity is what holds the ocean down. It keeps seawater wrapped around the planet instead of letting it drift away into space. The moon's gravity is much smaller by comparison, so it cannot simply lift the sea off Earth. But the moon's uneven pull across the planet is enough to slightly reshape the ocean at a planetary scale. That is the subtle beauty of tides. They are not caused by gravity overpowering Earth's hold on the ocean. They are caused by the moon adding a small, uneven gravitational influence across a huge rotating world covered in mobile water. When the scale is planetary, small differences matter. A force too gentle to notice in a cup of water can help rearrange enormous ocean basins when it acts across thousands of kilometres. This is why tides should not be imagined as water being pulled upward in one neat place beneath the moon. The real situation is more like Earth, being gently stretched along the Earth-Moon line. The ocean responds to that stretching because water can flow, shift, pile up, and move around continents and basins. The result is not a single mound of seawater chasing the moon, but a global tidal pattern shaped by uneven gravity. The moon's pull is quiet, distant, and invisible, but it is not vague. It follows the rules of universal gravitation. It weakens with distance. It acts on Earth's near side, centre, and far side with slightly different strength. And from those small differences comes one of the grandest regular motions on the planet. Every tide begins with that uneven pull, not a hand lifting the sea, not the moon scooping water into the sky, but Earth itself being subtly stretched beneath a grey companion nearly 400,000 kilometres away. The ocean feels that stretching most clearly, and the shoreline records it hour by hour as the water rises, pauses, and falls again. It is easy to imagine tides as a single swelling of water directly beneath the moon. After all, if the moon pulls on the ocean, then surely the ocean should rise on the moon-facing side of Earth, and that should be the main event. The moon is over there. The water is pulled that way. One moon, one pull, one bulge. It sounds tidy, and tidy explanations are very tempting. Unfortunately, nature has a habit of looking at tidy explanations and adding a second bulge just to keep everyone humble. The real tidal pattern is more subtle. In the simplest version, Earth has two broad tidal bulges, one on the side facing the moon and another on the far side of the planet. This can feel strange at first. The near-side bulge seems to make sense because that side of Earth is closer to the Moon and feels a slightly stronger lunar pull. But the far side bulge raises the obvious question: why would the ocean rise on the side facing away from the Moon? The answer comes back to uneven gravity. The Moon pulls most strongly on the near side of Earth, a little less strongly on Earth's centre, and a little less strongly again on the far side. So compared with Earth's centre, the near-side ocean is being pulled slightly more toward the Moon. That helps create a bulge on the Moon-facing side. But on the far side, something different is happening. Earth's centre is being pulled toward the Moon slightly more, strongly than the far side ocean is. In that sense, the solid Earth is being pulled a little away from the far side water. This does not mean the far side ocean is being flung outward by some mysterious force. It is not being thrown away from Earth like a loose sock in a cosmic washing machine. The far side bulge is better understood as part of the same stretching effect. The whole Earth-Moon system is under uneven gravitational acceleration. The near side, centre and far side are all responding to the Moon's gravity, but they are not responding equally. That difference creates a stretching pattern along the line between Earth and the Moon. There is another useful idea here. Earth and the Moon do not simply behave as if Earth sits perfectly still while the Moon circles politely around it. Both bodies orbit a shared centre of mass called the barycenter. Because Earth is much more massive than the Moon, this barycenter lies inside Earth, but not exactly at Earth's centre. Earth makes a small monthly wobble around that shared point, while the Moon makes a much larger orbit around it. This shared motion matters because the Earth-Moon system is not just a Moon pulling on a motionless ocean, it is a gravitational partnership. Earth and the Moon are both moving around their barycenter, while gravity varies across Earth's width. When people try to explain the far side tide using only a simple outward force, the picture can become misleading. The cleaner explanation is that tidal forces come from differences in gravitational pull across Earth. The ocean is not pushed away on the far side by magic. It is part of a planet-wide stretching pattern caused by the geometry of gravity. A gentle visual image may help. Imagine a long, soft object being stretched along its length. One end is pulled a little more than the middle, and the middle is pulled a little more than the other end. The shape changes not because every point is pulled in the same way, but because different parts are accelerated differently. Earth's oceans respond to this difference, especially because water can move more easily than rock. The sea adjusts, flows, piles up, and settles into tidal patterns shaped by the Moon's uneven pull. Of course, the classic picture of two neat tidal bulges is still a simplification. In diagrams, those bulges are often drawn as huge, smooth, football-shaped swellings around Earth. Real tides are not that clean. The actual height of open ocean tides is much smaller than those diagrams suggest, often less than a metre in many deep ocean regions, before coastlines and shallow seafloors amplify or reshape them. Continents get in the way. Ocean basins have different depths. Water has inertia. Earth rotates. The seafloor drags on moving water. The result is far more intricate than two perfect watery hills calmly sitting on opposite sides of the planet. Still, the two-bulge idea is a useful doorway. It corrects the common misunderstanding that the Moon creates only one high tide directly beneath it. It shows that tides are not simply about water being lifted in one place, but about Earth and its oceans being gently stretched along the Earth-Moon line. Then Earth turns. As the planet rotates, different coastlines move through this broad tidal pattern. A shore may pass into a region of higher water, then later into a region of lower water, then into higher water again. This is why many places experience roughly 2 high tides and 2 low tides over a little more than one ordinary day, though local geography can alter the exact rhythm. The Moon's pull is not making a single travelling lump of water chase it around Earth. It is creating a gravitational stretching pattern, and Earth rotates through that pattern. From the shoreline, that becomes something beautifully simple to watch. The water arrives, the water pauses, the water leaves, and somewhere far above, the moon continues its quiet work. The tide can look as if it is travelling obediently around Earth, beneath the moon, like a wave being dragged across the planet by an invisible rope. It is a tempting picture, because it feels simple. The moon is overhead, the water rises. The moon moves on, the water follows. The ocean becomes a sort of loyal but very damp pet, circling the globe on a lunar lead. But real tides do not work quite so neatly. The moon creates a broad tidal pattern through its uneven gravitational pull, but Earth is also rotating beneath that pattern. Every beach, harbour, island, estuary and coastline is being carried around by Earth's spin. So the tide experienced at one place is not simply a wave arriving from the moon. It is the result of that location rotating through regions of higher and lower water, shaped by the Earth-Moon relationship. This is why the timing of the tides is connected to something called the lunar day. An ordinary solar day is based on Earth rotating once relative to the Sun, which takes about 24 hours. But the moon is not fixed in place while Earth turns. It is also moving along its orbit around Earth. By the time Earth has completed one rotation relative to the Sun, the moon has shifted a little farther along its path. A location on Earth must rotate a bit extra before it faces the moon in roughly the same way again. That extra time means the lunar day is about 24 hours and 50 minutes. This is one of the reasons tides usually arrive a little later each day. The sea does not run on the exact same clock as the sun. It is following the moon's slightly slower rhythm. The tide table quietly drifts from day to day, which is why high tide at a harbour might be in the morning one day, later the next, and later still after that. The moon is not late exactly. It is just using its own calendar, which is a very moon-like thing to do. In many places, this produces 2 high tides and 2 low tides during a lunar day. These are called semi-diurnal tides. The word means that the tide cycle happens roughly twice in a day. Many coastlines along the Atlantic experience this pattern clearly, including large stretches of the eastern coast of North America and Western Europe. A harbour may rise to high tide, fall to low tide, rise again, and fall again across a period a little longer than 24 hours. But not every coastline follows this pattern so neatly. Some places have diurnal tides, with one main high tide and one main low tide during a lunar day. Parts of the Gulf of Mexico show this kind of behaviour. Other places have mixed tides, where 2 high tides and 2 low tides occur, but the heights are noticeably unequal. This is common along many parts of the Pacific coast. One high tide may be much higher than the other, and one low tide may expose far more shore than the next. These differences happen because the real ocean is not a smooth global bathtub. Earth's continents block and redirect water. Ocean basins have different shapes and depths. Some coastlines face broad open water, while others sit inside bays, gulfs, channels, or island chains. Water has inertia, so it does not instantly adjust to the moon's pull. It sloshes, rotates, reflects, drags against the seafloor, and responds to the shape of the basin around it. So the simple idea of Earth turning through tidal bulges is useful, but it is only the beginning. It explains why tides are connected to Earth's rotation and the moon's position. It helps explain why many places have 2 high tides and 2 low tides in a little over one ordinary day. But the exact schedule at any particular coast depends on the ocean basin that delivers the tide there. The Atlantic, the Gulf of Mexico, and the Pacific all sit under the same moon, yet their tides can behave very differently. The moon sets the main rhythm, but local geography changes the music. One coastline receives a strong, regular beat, another receives a slower pulse, another gets something uneven, as if the ocean is quietly improvising. At the shore, this becomes the familiar daily pattern of water arriving and leaving, but behind that gentle motion is a rotating planet, an orbiting moon, and enormous ocean basins reshaping a gravitational rhythm into local time. The tide is not just moving around Earth. Earth is turning through the tide, carrying every coastline through the moon's quiet influence, one shoreline at a time. The moon is the main character in the story of the tides, but it is not the only body in the sky with a role to play. The sun also pulls on Earth's oceans. Every day, every ocean, every coastline, and every drop of seawater is held within the gravitational influence of both the moon and the sun. The moon may be the closer companion, moving around Earth like a quiet clock in the night, but the sun is enormous. It contains nearly all the mass in the solar system, and its gravity is the reason Earth stays in orbit rather than wandering off into space like a lost marble with poor planning, skills. So it is natural to wonder why the moon has the stronger effect on Earth's tides. If the sun is so massive, why does it not dominate the ocean completely? The answer lies in distance. The sun's total gravitational pull on Earth is much stronger than the moon's total gravitational pull. That is why Earth orbits the sun, while the moon orbits Earth. But tides are not controlled only by the total strength of gravity. Tides are created by tidal force, and tidal force depends on how much gravity changes from one side of Earth to the other. That change is strongly affected by distance. The closer an object is, the more noticeably its pull changes across Earth's diameter. The moon is much smaller than the sun, but it is also much closer. On average, the moon is about 384,000 kilometers away. The sun is about 150 million kilometers away. Because the sun is so distant, its gravity is more evenly spread across Earth. The near side of Earth and the far side of Earth are almost the same distance from the sun compared with the enormous Earth-Sun distance. There is still a difference, but it is smaller. The moon, being close, produces a larger difference in gravitational pull between Earth's near side and far side. That difference is what matters for tides, so even though the sun's gravity is far stronger overall, the moon produces the stronger tidal effect on Earth's oceans. The nearby small companion wins this particular contest against the distant giant, which is a nice reminder that in physics, as in finding the television remote, closeness can matter a great deal. Still, the sun's tidal influence is not small enough to ignore. It is the second major astronomical force shaping Earth's tides. The sun produces its own solar tide, a weaker tidal pattern that combines with the stronger lunar tide. Sometimes the solar tide and lunar tide reinforce one another. Sometimes they partly work against one another. The result is a regular change in the tidal range, meaning the difference between high tide and low tide. When the sun, moon, and Earth are roughly aligned, their tidal effects combine. This happens near new moon, when the moon lies roughly between Earth and the sun, and near full moon, when Earth lies roughly between the sun and the moon. At these times, the lunar and solar tidal forces pull along roughly the same line. The ocean responds with a larger tidal range. High tides tend to be higher, and low tides tend to be lower. These are called spring tides. The name can be a little misleading. Spring tides do not only happen in spring. They happen throughout the year. The word spring here is closer to the idea of the water springing or rising more strongly. So if someone hears spring tide in the middle of winter, there is no need to accuse the ocean of seasonal confusion. It is behaving exactly as it should. When the moon is near first quarter or last quarter, the situation changes. The sun and moon are then pulling at roughly right angles from Earth's point of view. Their tidal effects partially counteract each other. The moon is still producing the stronger tide, but the sun is reducing the overall contrast between high and low water. These smaller tidal ranges are called neap tides. During neap tides, high tides are usually not as high, and low tides are usually not as low. This pattern is one of the reasons the moon's phases are so useful for understanding tides. The phase of the moon does not change the moon's gravity. A full moon is not gravitationally stronger than a crescent moon. What changes is the alignment of the moon, Earth, and Sun. The visible shape of the moon is a clue to the geometry of the system, so the moon controls the ocean most strongly, but not alone. The ocean is being shaped by a gravitational partnership. The moon sets the dominant tidal rhythm because it is close enough for its gravity to vary significantly across Earth. The sun adds a second rhythm, weaker but still powerful, changing the size of the tides through alignment. Together they create the familiar cycle of spring tides and neap tides, a pattern written into tide tables, harbour routines, coastal ecosystems, and the slow daily movement of the sea. Every high tide, then, carries more than one influence. It is not only the moon pulling from nearby space, it is also the sun, distant and massive, adding its quieter hand to the ocean's motion. The moon leads the rhythm, but the sun changes the volume, and between them Earth's oceans rise and fall in a pattern shaped by gravity across the sky. The moon's changing face is one of the easiest rhythms in the sky to notice. Some nights it is full and bright, rising like a pale lantern over roofs, fields, and water. Other nights it is only a thin crescent, delicate enough to look as though it has been carefully trimmed from silver. Between those shapes, it grows and fades through its familiar cycle, moving from new moon to first quarter, full moon, last quarter, and back again. The ocean follows that cycle too, not because the moon becomes heavier or lighter, but because the moon's phase tells us where it is in relation to Earth and the sun. That is the key point. The phase of the moon does not directly change the moon's gravity. A full moon is not pulling harder because it looks rounder. A crescent moon is not weaker because less of it seems visible. The moon has essentially the same mass throughout the month. What changes is its position. The shape seen from Earth is a visual clue to the geometry of the sun, moon, and Earth. When the moon is new, it sits roughly between Earth and the sun. The side lit by the sun is mostly facing away from Earth, so the moon itself is difficult to see. But gravitationally, something important is happening. The sun and moon are pulling in roughly the same line. Their tidal forces combine, and the ocean responds with a larger tidal range. High tides tend to be higher, and low tides tend to be lower. This is one of the times when spring tides occur. The same broad alignment happens at full moon, but with Earth between the sun and the moon. The visible side of the moon is fully lit because it is opposite the sun in the sky. Again, the sun, Earth, and moon lie roughly along one line. The solar tide and lunar tide reinforce each other, creating another spring tide period. This is why the strongest tidal ranges often cluster around new moon and full moon. The name spring tide can cause a small amount of understandable confusion. It does not mean a tide that only happens during spring. It can happen in winter, summer, autumn, or on a grey Tuesday when everyone is just trying to park near the harbour without consulting a naval almanac. The word spring here refers to the idea of the tide springing higher, or producing a larger range between high water and low water. Around first quarter and last quarter moon, the arrangement is different. From Earth, the sun and moon appear roughly at right angles to each other. The moon is pulling the ocean along one line, while the sun's tidal influence is acting along another. The two effects do not cancel completely, because the moon's tidal force is stronger, but they partially work against each other. The result is a smaller tidal range. High tides are usually not as high, and low tides are usually not as low. These are called neap tides. So the moon's phases act almost like a calendar for changing tide strength. New moon and full moon point toward spring tides. First quarter and last quarter point toward neap tides. The ocean is not only rising and falling across each lunar day, it is also breathing through a longer monthly rhythm. This is why tide tables are so useful. For sailors, harbour workers, fishers, coastal engineers, lifeboat crews, beach walkers, and people who simply do not wish to return from a pleasant stroll by accidentally becoming part of the estuary. Tide tables turn sky geometry into practical information. They show when high tide and low tide are expected, and they often reveal the changing strength of the tides across the month. A full moon near a coastline with a naturally large tidal range can matter very much. A neap tide in the same place may produce a gentler, narrower movement of water. Modern tide prediction uses far more than lunar phase alone. It includes astronomy, long-term observations, local geography, seafloor shape, tidal harmonics, atmospheric pressure, winds, and coastal conditions. But lunar phase remains a simple, visible sign of the larger alignment. It is the sky's way of showing the approximate arrangement that helps decide whether the ocean will move through a wider or narrower range. That makes the moon's face more than a beautiful nighttime detail. It is part of a moving system. The crescent, the half-lit moon, the full disk, and the invisible new moon each mark a different relationship between the main gravitational players. The ocean carries that relationship in water, not perfectly, not identically everywhere, and never as simply as a diagram suggests, but clearly enough that coastal people have watched it for thousands of years. The tide is therefore not just a daily rise and fall, it is also monthly. It keeps time with Earth's rotation, the moon's orbit, and the changing alignment of the sun. At the shore, that larger celestial rhythm becomes wet sand, floating boats, exposed rocks, and water slowly returning under the quiet light of the moon. The tidy textbook version of the tide is a useful place to begin, but it is not where the real ocean lives. In many simple diagrams, Earth is shown with two smooth tidal bulges, one facing the moon and one on the far side. The picture is not wrong as a first idea. It helps show that the moon's gravity stretches Earth and its oceans along the Earth-Moon line. It helps explain why many coastlines experience two high tides and two low tides across a lunar day. It gives the mind something clear to hold on to before the ocean politely ruins the simplicity. Real tides happen on a spinning, uneven planet covered by continents, islands, shallow shelves, deep basins, underwater ridges and coastlines that appear to have been designed by someone with a very relaxed attitude towards straight lines. The ocean is not wrapped smoothly around Earth like a perfect layer of water. It is broken into connected but irregular basins, interrupted by land and shaped by seafloor depth. So the tide cannot simply form two clean bulges and slide around the globe without obstruction. Continents are the first great complication. If Earth were covered by one uninterrupted ocean of even depth, this simple tidal picture would be closer to reality. But Earth has Africa, Eurasia, the Americas, Australia, Antarctica, countless islands, narrow channels, shallow seas, and twisting coastlines. These landmasses block the movement of water. They force tidal waves to reflect, bend, squeeze, slow down, speed up, and reorganize themselves. Ocean basins also have their own natural behavior. The Atlantic Ocean, the Pacific Ocean, the Indian Ocean, and the Southern Ocean are not just empty bowls with water sitting quietly inside them. Each basin has its own size, depth, shape, seafloor structure, and connection to neighbouring waters. These features give each basin its own rhythm. Some basins respond strongly to tidal forcing, while others respond more weakly. Some coastlines amplify the tide, while others soften it. This is where tide theory had to move beyond the simplest version of Isaac Newton's gravitational explanation. Newton identified the central role of gravity and showed why the moon and sun could create tides. But the full behaviour of real oceans needed a more dynamic theory. Pierre-Simon Laplace made a major step in that direction with his tidal equations, which treated tides not as static bulges, but as moving ocean waves affected by Earth's rotation, basin shape, water depth, and motion. Laplace's work helped reveal that real tides behave like long waves moving through ocean basins. These are not ordinary wind waves, the kind seen flickering across the surface on a breezy day. Tidal waves are enormous, shallow water waves, meaning their behaviour is strongly influenced by the depth of the water, compared with their very long wavelength. In the deep ocean, they may be broad and relatively low, but as they approach continental shelves, bays and estuaries, they can change dramatically. The seafloor matters because water moving over a shallow region behaves differently from water moving over a deep one. A shallow continental shelf can slow the tide and cause water to pile up. A narrowing bay can funnel the tide into a smaller space and increase the tidal range. A deep ocean basin can allow the tidal wave to move differently from a broad, shallow sea. The moon provides the gravitational rhythm, but the shape of the ocean decides how that rhythm is expressed. Water also has inertia. It does not instantly leap into the exact position suggested by the moon's pull. It resists changes in motion. It keeps moving after being set in motion. It drags against the seafloor and coastlines through friction. It sloshes round basins, reflects from continental margins, and interacts with currents and underwater features. The result is that high tide does not always happen exactly when the moon is overhead. The ocean is not a perfectly obedient servant. It is more like a very large, very heavy dance partner who heard the music slightly late but is still doing its best. Coastline geometry adds still more complexity. A wide-open coast may receive the tide one way, while a long narrowing estuary may receive it very differently. A small island, a shallow shelf, a curved bay, or a strait can alter the timing and height of the tide. This is why tide tables are local. A tide table for one harbour cannot simply be used for another harbour a short distance away without correction, because the water's route, depth, and surroundings may be different. So the familiar textbook bulges are a doorway, not the whole building. They show the basic lunar stretching force, but real tides are moving, rotating, delayed, amplified, weakened, and redirected by the planet itself. The same moon shines over every ocean, but it does not produce the same tide everywhere. One coastline may see a modest rise and fall. Another may watch the sea climb several meters. Another may experience one clear high tide a day, while elsewhere the water rises and falls twice. Under the same moon, every shore receives its own version of the tide. The sky sets the rhythm, but the ocean, continents, and seafloor decide the local song. Some coastlines see the tide arrive gently, almost shyly, as a modest lift of water against a harbour wall. Others experience something far more dramatic. The sea withdraws so far that boats sit on the exposed floor of a bay, then returns with enough force and height to transform the entire landscape. Under the same moon, one place may see a quiet change of less than a metre, while another may see the ocean rise by many metres, as if the shore has been rewritten between breakfast and evening. This difference is called tidal range, meaning the vertical distance between low tide and high tide. It varies enormously around the world, not because the moon chooses favourite beaches, although some beaches are admittedly making a strong case, but because local geography can amplify or reduce the tide. The moon provides the main timing and gravitational forcing. The coastline decides how dramatic the performance becomes. One of the clearest examples is the Bay of Fundy, between Nova Scotia and New Brunswick in Canada. It is famous for having some of the largest tidal ranges on Earth, with tides that can rise and fall by more than 15 metres in certain places. That is taller than many houses, which is a fairly strong reminder not to leave your picnic blanket too close to the water and then wander off for several hours. The Bay of Fundy is not extreme simply because the moon pulls harder there. The moon's gravity is not especially enthusiastic over eastern Canada compared with everywhere else. The difference comes from the bay's shape, depth, and natural rhythm. The bay narrows as it reaches inland, creating a funnel effect. As the tide enters, a huge volume of water is squeezed into a smaller and shallower space. The water has nowhere to spread easily, so it rises higher. There's also resonance. In physics, resonance happens when a system is pushed at a rhythm, close to its own natural rhythm. A familiar example is pushing a swing. If the push comes at the right moment, the swing rises higher with less effort. Ocean basins and bays can behave in a similar way, although with rather more water and fewer playground arguments. The natural sloshing period of the Bay of Fundy is close enough to the timing of the incoming Atlantic tide that the water movement is amplified. The tide arrives, the basin responds, and the result is one of the most dramatic tidal environments on the planet. Narrowing bays are not the only places where tides grow larger. Shallow continental shelves can slow incoming tidal waves and cause water to pile up. Gently sloping coastlines can allow a modest vertical rise to cover a huge horizontal distance. Estuaries can squeeze tidal water into narrower channels, increasing its height and speed. The same incoming tide that seems ordinary offshore can become much more powerful when it enters the right coastal shape. The Severn Estuary between England and Wales is another strong example. It has one of the largest tidal ranges in the world, partly because of its narrowing funnel shape and broad, shallow channels. At certain times, especially around large spring tides, the incoming tide can form the Severn Bore, a tidal wave that travels upstream against the river's flow. This happens when the rising tide is forced into an increasingly narrow and shallow river channel, creating a moving wave front. It is dramatic, but it is still part of the same larger story. Lunar and solar tidal forcing shaped by local geography. Other places have much smaller tides for the opposite reasons. Some seas and coastlines are arranged in ways that reduce the ocean's response. The Mediterranean Sea, for example, generally has a small tidal range compared with many Atlantic coasts, partly because its connection to the open ocean is narrow, and its basin dynamics do not amplify the tide in the same way. Some islands and oceanic coastlines also experience modest tides, because the surrounding basin shape, water depth, and local wave patterns do not pile the water up strongly against the shore. This is why tide behaviour can change so much from one coastline to another. The moon sets the broad gravitational rhythm. The sun modifies it. Earth's rotation bends and complicates it. But the final tide that appears at a harbour, beach, bay, estuary or mudflat depends on the local arrangement of land and sea. So when the ocean rises spectacularly in the Bay of Fundy or rushes into the Severn Estuary, it is not because the moon has suddenly become stronger. It is because the moon's steady pull is being translated through a particular coastal shape. The planet is full of irregular edges, shallow shelves, deep basins, narrow mouths, and winding estuaries, and each one turns the same celestial rhythm into something local. The moon controls the ocean indirectly. It does not micromanage every wave, channel, and harbour, like an exhausted cosmic harbour master with a clipboard. It provides the gravitational pulse. Then Earth's messy geography turns that pulse into real tides, small in some places, immense in others, and always shaped by the meeting of sky, sea, and shore. There is a hidden motion in the tides that is almost impossible to see from the shore. Standing beside the sea, the tide usually looks like water coming in and going out. It rises against a wall, covers a beach, fills an inlet, and later drains away again. From that point of view, the ocean seems to be moving toward the land and then away from it, as if the coast is breathing. That is true locally, but across whole ocean basins, tides often behave in a much stranger way. They do not simply slosh back and forth, they rotate. These rotating tidal systems are called amphidromic systems. An amphidromic system is a large tidal pattern in which the tide wave moves around a central point in the ocean. That central point is called an amphidromic point. Near an amphidromic point, the tidal range can be very small, sometimes close to zero, meaning the water level hardly rises and falls there at all. Around it, the tide wave rotates, and the tidal range generally grows larger with distance from the centre. It is a little like watching a sheet of water slowly turn around a quiet pivot. The centre barely moves up and down, while the edges experience a stronger rise and fall, not because there is a little plug hole in the ocean, of course, or a secret moon-powered whisk stirring the sea beneath the waves. The pattern comes from the way tidal waves move through rotating ocean basins. A major reason this happens is the Coriolis effect. The Coriolis effect arises because Earth is rotating. When water moves across the surface of a spinning planet, its path is deflected relative to the ground beneath it. In the northern hemisphere, moving water is deflected to the right of its direction of travel. In the southern hemisphere, it is deflected to the left. This does not mean the water is being grabbed sideways by a mysterious force. It means that motion on a rotating planet does not appear the same as motion on a still surface. The Coriolis effect is important for many large-scale motions on Earth. It helps shape weather systems, ocean currents, and tidal waves. With tides, it helps turn what might have been a simple back-and-forth movement into a rotating basin-wide pattern. When the moon's gravitational forcing sets ocean water in motion, Earth's rotation bends that motion. Continents, seafloor shape, ocean depth, and basin boundaries then reshape it further. The result can be a tide wave rotating around an amphidromic point. In the North Atlantic, for example, tidal patterns include amphidromic systems that help explain why tides arrive at different times and with different strengths around surrounding coastlines. In parts of the North Sea, the tide rotates around amphidromic points, so high tide does not happen everywhere at once. One coast may be approaching high water while another is already falling toward low water. The pattern is not random. It is the behaviour of a very large wave moving through a rotating irregular basin. This is one reason tide maps can look so different from the simple two-bulge picture. The moon still supplies the main gravitational rhythm, but once that rhythm enters the real ocean, it becomes transformed. The ocean does not respond as a smooth global shell. It responds through enormous moving waves, rotating around quiet centres, delayed by basin shape, slowed by shallow shelves, and redirected by land. The same lunar pull becomes a different local tide depending on where the coastline sits within the larger amphidromic system. Oceanographers map these hidden patterns using several tools. Tide gauges measure sea level at fixed coastal locations, creating long records of rising and falling water. Satellite altimetry measures sea surface height from orbit by timing signals reflected from the ocean surface. NASA, the European Space Agency, and other space agencies have supported satellite missions that help measure the shape and movement of the sea with remarkable precision. National oceanographic institutions then combine those observations with numerical models, allowing scientists to simulate how tides move through real ocean basins. These models are important because amphidromic systems cannot be understood properly from one beach alone. A single harbour shows the local result, but the full pattern stretches across hundreds or thousands of kilometres. To see the hidden spin of the tide, scientists need observations from many places, along with mathematics that can account for gravity, Earth's rotation, seafloor depth, friction, coastlines, and the geometry of the basin. The result is a quieter and more intricate picture of lunar control. The moon does not simply pull a mound of water across Earth. Its gravity sets the ocean in motion, and then Earth's rotation and geography turn that motion into broad, rotating systems. Some places sit near points where the tide hardly rises at all. Others sit near edges where the same rotating wave produces a much larger rise and fall. So beneath the familiar sight of water arriving at the shore, there is a hidden spin. The ocean is turning through patterns too broad for human eyes to see from land. The moon begins the motion, but the rotating Earth gives it shape, and the basins of the world guide it into great slow waves circling around almost still points in the sea. The tide is often imagined as a simple rising and falling of the ocean surface. From the beach, that is exactly what it looks like. The waterline creeps up the sand, reaches its highest point, pauses, and then slips away again. A harbour wall that was dry becomes wet. A rock pool disappears beneath the returning sea. A boat rises on its mooring as if lifted by a slow, invisible platform. The eye naturally follows the vertical motion, because that is the easiest part to notice. But tides are not only about water moving up and down. A tide affects the ocean as a whole. As sea level rises in one place and falls in another, water has to move horizontally. It flows through channels, around headlands, across shallow shelves, into estuaries and out again. This sideways motion is called a tidal current, and in many places it is the most powerful and practical part of the tide. High tide and low tide describe the level of the water. Flood tide and ebb tide describe the movement of the water. A flood tide is water moving in as the tide rises. An ebb tide is water moving out as the tide falls. That distinction matters because the ocean can be moving strongly even when the water level itself seems calm. A harbour may look peaceful from a distance while powerful tidal currents are flowing below the surface. In narrow places where large volumes of water have to squeeze through limited space, these currents can become especially fast. The moon's pull creates the broader tidal rhythm, but coastlines and channels turn that rhythm into moving rivers of seawater. The English Channel is a good example. It is a busy, shallow sea passage between southern England and northern France, connecting the Atlantic Ocean with the North Sea. Tides moving into and out of this region create strong tidal streams that have mattered for navigation for centuries. Sailors crossing or travelling along the channel must account for the direction and timing of these currents, because the moving water can help carry a vessel along or push it away from its intended path. The sea is not just a surface to travel over. It is a moving body that can quietly argue with the map. Farther north, the Pentland Firth between mainland Scotland and the Orkney Islands is known for some of the strongest tidal currents in the world. As Atlantic water is driven between islands, headlands and channels, enormous volumes of seawater are forced through narrow passages. The result can be fast, turbulent tidal streams, whirlpools, standing waves, and rough conditions that demand real respect from sailors. The moon is still part of the underlying cause, but the local geography gives the movement its force and character. The Strait of Messina between Sicily and mainland Italy offers another example of complex tidal flow. Its narrow shape, changing depths, and meeting waters create strong currents and whirlpools that have been noticed since antiquity. Ancient stories of sea monsters such as Scylla and Charybdis likely grew around the real dangers of turbulent water in this region. It is a lovely reminder that before oceanography had instruments and equations, people still knew when a patch of sea was behaving badly and deserved a dramatic explanation. Tidal currents are important for many reasons. For navigation, they affect where and when ships can travel safely. A current running through a harbour entrance, estuary or strait can change a journey from easy to hazardous. For sediment transport, Tidal currents move sand, mud, silt and gravel, helping to build and reshape beaches, sandbanks, mudflats, salt marshes, and estuary channels. A coastline is not a fixed line. It is constantly being edited by water, and the tide is one of the editors. Marine ecosystems also depend on tidal movement. Tidal currents bring oxygen-rich water into coastal habitats. They carry plankton, larvae, nutrients, and organic matter. They flush estuaries, stir shallow seas, and help connect different parts of coastal environments. Many animals time their feeding, spawning, or movement around the flood and ebb of the tide. For them, the tide is not just a change in water height. It is a delivery system, a transport network, and sometimes a dinner bell with suspiciously wet manners. Coastal safety depends on this too. A beach that seems calm at low tide may be cut off by a fast incoming flood tide. A narrow channel may become dangerous when the ebb tide flows against wind or waves. Rip currents, tidal races, and shifting sandbanks can all be influenced by the timing and strength of tidal flow. Understanding tides means understanding movement, not merely measuring height. So the moon's influence is not only vertical. It does not just make the sea rise and fall like water in a giant bowl. Much of tidal behaviour is sideways flow, the horizontal movement of seawater across a rotating, irregular planet. The tide lifts, lowers, pushes, pulls, pours, drains, stirs and carries. It moves through the ocean in 3 dimensions, from the visible surface to the currents that travel through channels and across shelves. This moving water helps explain why tides matter so deeply to the ocean itself. They do not only mark the edge of the shore, they stir the sea, move sediments, feed habitats, shape coastlines, and influence life. The moon's gravity begins the pattern, but the ocean turns that pattern into motion, and that motion carries through the living water. The ocean does not only move where it can be seen. At the surface, tides reveal themselves in familiar ways. The sea rises against a harbour wall, slides across mudflats, covers rocks, and then pulls away again. Tidal currents move sideways through channels and estuaries, carrying sediment, nutrients, and boats that may or may not be going exactly where the person steering them had hoped. But below all of that visible movement, the moon is also helping stir the hidden interior of the ocean. These hidden motions are called internal tides. Unlike surface tides, which raise and lower the boundary between ocean and air, internal tides move along boundaries inside the ocean itself. They occur where layers of seawater with different densities meet. The ocean may look like one continuous body of water, but it is often arranged in layers, shaped by temperature and salinity. Temperature affects density because colder water is usually denser than warmer water. Salinity affects density because saltier water is usually denser than fresher water. Together, temperature and salinity create a layered ocean, with lighter water often sitting above denser water below. These layers are not rigid shelves, of course. The sea is not secretly stacked like a very damp cake, but the density differences are real enough to guide motion. Where lighter water rests above heavier water, an internal boundary can form. Oceanographers often describe this as stratification, meaning the water column has layers with different properties. Along these boundaries, waves can travel, not at the surface, but deep inside the sea. The moon helps create these internal waves when tidal currents move across rough underwater landscapes. The seafloor is not flat. It has continental slopes, underwater ridges, seamounts, trenches, plateaus, and mountain chains hidden beneath the water. When tidal flow pushes dense and lighter layers across these shapes, the water can be lifted and disturbed along internal boundaries. That disturbance can generate internal tides, which then travel away through the deep ocean. A seamount, for example, can act like an obstacle in the path of tidal flow. As water moves over and around it, layered water is displaced upward and downward. A continental slope can do something similar, forcing tidal energy into internal waves. Underwater ridges, such as those found across many ocean basins, can convert part of the ordinary tide into deep internal motion. The moon's gravity begins the rhythm, but the seafloor turns some of that rhythm inward, sending waves through the ocean's hidden layers. These internal tides can be enormous. Their vertical motion inside the ocean may be far larger than the surface tide visible above them, even though a person floating at the surface might notice very little. They can travel long distances through the deep sea, carrying energy away from the places where they formed. Eventually, some of that energy breaks down into turbulence and mixing. This mixing matters. Without it, the ocean would be more strongly separated into layers, with less exchange between warm upper waters and colder deep waters. Internal tides help move heat, nutrients, oxygen, carbon, and dissolved substances between layers. They contribute to the slow stirring that keeps the ocean from becoming too neatly organized. And if the ocean has taught us anything, it is that it has very little interest in being neatly organized for our convenience. Ocean mixing is important for marine life because nutrients from deeper water can help support plankton growth near the surface when they are brought upward. It is also important for climate because the ocean stores and transports vast amounts of heat. The way heat moves through the ocean affects circulation patterns, regional climates, sea surface temperatures, and the long-term exchange of energy between ocean and atmosphere. Internal tides are only one part of that complex system, but they are a meaningful part. Institutions such as Woods Hole, Oceanographic Institution, and Scripps Institution of Oceanography have played major roles in studying ocean circulation, internal waves, seafloor processes, and deep ocean mixing. Research ships, moored instruments, underwater sensors, floats, and satellite observations all help scientists understand how energy moves through the ocean. Much of this activity is invisible from shore, but it is central to how the sea works as a planetary system. The quiet surprise is that the moon's influence reaches into this hidden world. It does not only raise water along beaches, it does not only create tidal currents through harbours and straits. By driving tidal motion across the seafloor, it helps generate internal tides that stir the ocean's interior. The same gravitational rhythm that lifts boats in a harbour can also send waves along density layers far below the surface, where sunlight never reaches and the ocean moves in slower, darker patterns. So the moon controls more than the edge of the sea. Its pull becomes surface tide, tidal current, deep wave, and internal stirring. At the shoreline, the tide looks like a line of water arriving and leaving. In the deep ocean, that same rhythm becomes motion within layers, mixing heat and nutrients through the hidden body of the sea. The moon's control is quiet, indirect, and transformed by Earth itself, but it reaches much farther down than the eye can follow. The edge of the sea is never truly finished. A coastline may look like a boundary, a clean line where land ends and ocean begins, but in reality it is one of the most restless places on Earth. The tide arrives, lifts the water, pushes into creeks and channels, covers mud and sand, then drains away again, carrying tiny pieces of the land with it. Grain by grain, current by current, the shoreline is revised, sometimes gently, sometimes with all the subtlety of a very wet editor who's decided the previous draft was unacceptable. Tides help shape the physical edges of continents by moving sediment. Sand, silt, clay, shells, organic matter, and small fragments of rock can be lifted, carried, dropped, and lifted again. A flood tide may push sediment inland or upstream. An ebb tide may draw it back toward the sea. Over time, this repeated motion can build mudflats, reshape sandbanks, deepen channels, and shift the position of beaches. In places where tidal currents are strong, the seabed itself can be patterned into ripples and bars, like a hidden landscape written by moving water. Tides also contribute to erosion. When tidal movement combines with waves, currents, and weather, cliffs and banks can be worn away. The tide changes where waves strike the land, raising and lowering the level at which wave energy is delivered. A cliff may be attacked at different heights across the tidal cycle, while loose material at its base is carried away. The moon is not standing offshore with a chisel, naturally, but its rhythm helps decide when and where water reaches the land. Estuaries show this process especially clearly. An estuary is a place where river water and seawater meet and mix. Fresh water flows down from the land, carrying sediment and nutrients. Salt water pushes in from the sea with the tide. The result is a shifting environment of channels, mudflats, sandbanks, marshes, and brackish water, where salinity changes from place to place and hour to hour. Estuaries are among the most productive environments on Earth because they receive nutrients from both land and sea, while their sheltered waters provide feeding and nursery grounds for many species. The Thames estuary is one example of a tidal landscape shaped by this meeting of river and sea. As the River Thames widens toward the North Sea, tidal movement influences water levels, sediment transport, navigation, flood risk, and wetland habitats. The estuary is not simply a river mouth, it is a living, moving zone where the tide pushes inland and the river pushes outward, each one altering the other. The Wadden Sea, along the coasts of the Netherlands, Germany and Denmark, is another powerful example. It contains vast tidal flats, channels, salt marshes, and barrier islands. At low tide, broad areas of mud and sand are exposed. At high tide, much of that landscape disappears beneath shallow water. This repeated flooding and draining supports huge numbers of worms, shellfish, fish, birds, and microorganisms. The place is almost like a dining table that the sea lays out twice a day, although the menu is mostly mud, which is excellent news if you are a wading bird. The Bay of Fundy also shows how tides can help shape a landscape over long periods. Its enormous tidal range moves vast volumes of water through bays, channels, and mudflats. Cliffs, salt marshes, tidal flats, and estuarine environments that all carry the mark of repeated tidal action. The moon provides the underlying rhythm, but the bay's shape turns that rhythm into one of the most dramatic coastal systems on Earth. Tidal flats, salt marshes, and mangrove systems depend on regular flooding and draining. Tidal flats are exposed at low tide and covered at high tide, creating feeding grounds for birds and habitat for burrowing animals. Salt marshes develop where fine sediment accumulates, and salt-tolerant plants take root, slowing water, trapping more sediment, and building rich coastal wetlands. Mangrove forests found in warmer regions grow in tidal zones where their roots stabilize muddy shores, shelter young fish, and protect coastlines from waves and storm energy. But tides do not act alone. Coastlines are shaped by many forces at once. Waves deliver energy from wind. Storms can rapidly erode beaches and flood low land. Rivers bring sediment from inland landscapes. Sea level changes alter where the ocean reaches. Geology controls whether the coast is made of hard rock, soft clay, sand, limestone, or volcanic material. Human activity also changes coasts through harbours, seawalls, dredging, drainage, and land reclamation. The tide is one powerful actor in a crowded play. Still, over years, centuries, and longer stretches of time, the moon's influence becomes written into coastal geography. It appears in tidal creeks winding through marshes, in mudflats exposed beneath wide skies, in estuary channels, in sandbanks, in mangrove roots, and in the daily flooding and draining of low coastal land. the pull of a distant moon becomes a shape on Earth, and once the coast is shaped by tides, life responds. Plants, animals, birds, fish, shellfish, and microorganisms all find opportunities in the moving boundary between land and sea. The tide does not only sculpt the shore, it creates habitats, schedules, feeding times, dangers, shelters, and rhythms that living things learn to follow. The moon's gravity becomes landscape, and then landscape becomes home. Life at the edge of the sea has to be good at change. The intertidal zone is the strip of coast between high tide and low tide, and it is one of the most restless habitats on Earth. For part of the day it is underwater, for another part it's exposed to air, sunlight, wind, rain, heat, cold, and the occasional curious human peering into a rock pool as if expecting a tiny sea monster to introduce itself. Few places ask so much of the organisms that live there. The tide brings food, oxygen, moisture, and movement. Then it leaves, taking the cover of water with it. To survive here, life has evolved around the rhythm of the tide. Barnacles clamp themselves to rocks and close their hard plates when exposed, keeping moisture inside until seawater returns. Mussels anchor themselves with strong threads, forming dense beds that resist waves and drying. Limpets grip the rock tightly with their muscular foot, reducing water loss and protecting their soft bodies beneath a tough shell. Sea anemones pull in their tentacles when the tide goes out, becoming small closed blobs until the water comes back and they can open again like patient little underwater flowers. Crabs move with the changing shore, hiding in crevices, burrowing into sand, feeding when water covers the flats, or scuttling across exposed ground while the tide is low. Rock pool fish may become trapped in small pools between tides, surviving changes in temperature, oxygen, and salinity until the ocean reconnects them to the wider sea. Shorebirds, such as oystercatchers, curlews, redshanks, and sandpipers, often feed at low tide, when mudflats and sandflats are exposed and full of worms, shellfish, and small crustaceans. The retreating sea becomes a buffet, although admittedly one with more mud than most restaurants would consider ideal. These behaviours are not random reactions. Many coastal organisms have internal timing systems linked to tidal cycles. One important idea is the circadial rhythm. A circadial rhythm is a biological rhythm that roughly follows the timing of the tides, usually a little over 12 hours between repeated tidal conditions, in places with 2 high tides and 2 low tides each lunar day. This sits alongside the more familiar circadian rhythm, which follows the roughly daily pattern of light and darkness. Circadian rhythms help organisms respond to day and night. Circadial rhythms help coastal organisms respond to the ocean's coming and going. An animal living in the intertidal zone may need to know not only whether it is night or day, but whether the sea is about to return, whether it is safe to feed, whether it should close up, burrow down, move out, or wait. In this environment, timing can be the difference between feeding and drying out, or between hiding safely and being collected by a hungry bird with excellent punctuality. Chronobiology, the study of biological rhythms, and marine biology have both explored these tidal clocks. Researchers have studied tidal rhythms in crabs and other intertidal organisms, showing that some behaviours can continue in laboratory conditions, even when the animal is removed from the shore. That suggests an internal rhythm, not merely an instant response to wetness or dryness. The organism carries something of the tide within its own biology, at least for a time. This does not mean the moon is consciously directing life. The moon is not leaning over the planet issuing tiny instructions to barnacles, crabs, mussels, and shorebirds. It is not a celestial manager of coastal scheduling, which is probably for the best. What the moon does is create a reliable environmental rhythm through gravity. The ocean rises and falls, Habitats flood and drain. Food appears and disappears. Predators gain and lose access. Conditions shift in repeated patterns. Natural selection can then favour organisms that respond well to those patterns. Over many generations, life adapts to what repeats. In the intertidal zone, the repeated pattern is not only sunlight and darkness, but immersion and exposure. The tide creates alternating worlds. Underwater, an animal may feed, breathe through gills, release larvae, or drift with currents. Exposed to air, the same animal may need to seal itself, cling tightly, tolerate heat, conserve water, or hide from birds. Plants and algae also face this rhythm, coping with drying, sunlight, salt, and wave energy. Tidal habitats are therefore shaped by both physics and biology. Gravity creates the rhythm. Water carries the rhythm to shore. Rocks, mudflats, marshes, mangroves, and pools hold the rhythm in place. Living things then build their behaviour, bodies, and timing around it. The moon's influence becomes more than a movement of seawater. It becomes part of feeding schedules, breeding cycles, sheltering habits, migration patterns, and the structure of coastal ecosystems. So when the tide rises beneath moonlight, it is not only changing the height of the sea, it is opening doors for some creatures and closing them for others. It is covering mussel beds, lifting seaweed, filling pools, stirring larvae, and setting shorebirds on the move when the water withdraws again. The ocean follows the moon, and along the edges of that ocean, life has learned to follow the tide. The edge between sea and land is not only a place where water rises and falls, it may also have been one of the great testing grounds in the history of life. For most of Earth's story, life belonged to water. The earliest living systems evolved in aquatic environments, and for billions of years the land was mostly bare, exposed, and difficult. Water offered support, chemical stability, and protection from drying out. Land offered light, space, gases, minerals, and eventually new habitats, but it also brought serious problems. Any organism moving into that world had to cope with gravity in a new way, hold on to moisture, exchange gases in air, tolerate ultraviolet light, and survive surfaces that could dry, heat, cool, flood, and change quickly. Tidal environments may have played an important role in that long transition. This does not mean that tides single-handedly marched life onto land in a neat, heroic procession, with a crab at the front waving a tiny flag. Evolution is not that tidy, but intertidal zones create repeated wet and dry conditions, and those repeating conditions may have offered both opportunities and pressures for organisms living near the shore. A tidal, flat, shallow pool, marshy edge, or rocky shore can be underwater for part of the day and exposed later. Organisms in such places may experience immersion, drying, fresh water from rain or rivers, seawater from the tide, sunlight, oxygen, temperature shifts, and changing chemistry. Pools can become saltier as water evaporates, fresher after rain, warmer under sunlight, and poorer in oxygen during still periods. Then the returning tide refreshes them, reconnecting them with the wider sea. This kind of environment can encourage flexibility. Life in the intertidal zone must deal with change again and again. A creature or microbial community that survives a short exposure to air may gain access to new resources. A plant-like organism or microbial mat that tolerates drying may spread across damp surfaces. An animal that can crawl, cling, breathe, or shelter for a while outside open water may reach food or safety that fully aquatic organisms cannot easily use. The broader framework for understanding this is Charles Darwin's theory of evolution by natural selection. Darwin showed that organisms vary, that some variations affect survival and reproduction, and that useful traits can become more common across generations. In a tidal setting, natural selection would not be aiming toward land life in a planned way. It would simply favour traits that helped organisms survive the conditions around them. Over enough time, small advantages in drying tolerance, movement, gas exchange, anchoring, protection, or reproduction could matter. Microbial mats were among the earliest communities to colonize wet surfaces and shallow environments. These layered communities of microorganisms can trap sediment, change local chemistry, and survive in conditions that shift between wet and exposed. Later, plants began to spread onto land, gradually evolving structures and life cycles suited to air, sunlight, and soil. Arthropods, including early relatives of insects, spiders, and crustaceans, also became important land colonizers, bringing jointed limbs, tough outer coverings, and flexible behaviors into terrestrial environments. Vertebrates came later. The movement of vertebrate life onto land involved fish-like animals living in shallow water, floodplains, wetlands, and near-shore environments, with fins, lungs, or lung-like organs, and body forms that could eventually support movement in very shallow water and on land. Fossils such as Tiktaalik are often discussed because they show a mixture of fish-like and land vertebrate-like features. But this transition was not one sudden leap from ocean to beach. It was a long branching process across many environments, including rivers, swamps, lagoons, coastal wetlands, and possibly tidal settings. The important point is caution. Tides may have helped create useful environments for some transitions, but they were not a single settled explanation for life's movement onto land. Scientists discuss many contributing factors: oxygen availability, predator avoidance, access to food, shallow water habitats, plant colonization, changing climates, freshwater systems, coastal wetlands, and evolutionary accidents. The story is not a simple ladder from sea to shore. It is more like a vast, tangled shoreline of possibilities, with many paths explored and most of them leaving only faint traces. Still, tidal environments are powerful because they sit between worlds. They are not fully marine and not fully terrestrial. They offer repeated exposure without permanent abandonment of water. They create shallow pools, damp mud, oxygen-rich surfaces, shifting salinity, and a regular cycle of challenge and relief. For life, such places can be difficult, but difficulty is often where adaptation becomes interesting. In that sense, the Moon's influence may reach deep into Earth's biological history. By raising and lowering the sea, it helped create zones where organisms repeatedly met the edge of land. Across immense spans of time, those edges may have offered chances to adapt, survive, spread, and change. The Moon did not direct evolution. It did not choose which creatures would leave the water. But by shaping tides, it helped shape the environments where some of life's great experiments could unfold. The Moon is not only moving the ocean in the present, it has also been quietly changing Earth's rotation for billions of years. This is one of the stranger consequences of tides. At the shoreline, the tide feels like a daily rhythm. Water arrives, water leaves, boats rise, mudflats appear, and somewhere a person with very optimistic shoes learns that the sea was not finished with the path just yet. But the same tidal forces that move seawater also create friction, transfer energy, and slowly alter the relationship between Earth and the Moon. The process is subtle on human timescales, but across geological time, it becomes enormous. The key idea is tidal friction. The Moon's gravity raises tides in Earth's oceans, and it also produces much smaller tides in the solid body of Earth itself. These are called solid Earth tides, because even rock can deform slightly under gravitational force. Earth is not perfectly rigid. it flexes. The ocean shifts more visibly, but the planet beneath it also responds. If Earth did not rotate, and if there were no friction or delays, the tidal bulges would line up neatly with the Moon. But Earth does rotate, and real tides are delayed and distorted by ocean basins, continents, seafloor friction, and the movement of water. Because Earth spins faster than the Moon orbits, Earth's rotation carries the tidal bulges slightly ahead of the line between Earth and the Moon. That small offset matters. The tidal bulge has mass, and because it sits slightly ahead of the Moon, it exerts a gravitational pull on the Moon. This pull gives the Moon a tiny forward tug along its orbit. At the same time, the Moon pulls back on the bulge, creating a torque that slows Earth's rotation. The word torque means a twisting effect, the kind of influence that changes rotation. Here, it acts on a planetary scale, with Earth, ocean, rock, and Moon all involved in a slow exchange of angular momentum. Angular momentum is the quantity that describes rotational motion. In this system, some of Earth's rotational angular momentum is gradually transferred to the Moon's orbital motion. As a result, Earth's spin slows very slightly, and the Moon moves a little farther away. This does not happen quickly. The length of a day increases by only a tiny amount over human lifetimes. But over hundreds of millions and billions of years, the effect adds up. In the distant past, Earth rotated faster and days were shorter. Geological evidence from ancient tidal deposits, coral growth patterns and sedimentary rhythms suggest that hundreds of millions of years ago, a day on Earth was noticeably shorter than it is now. The planet has been slowing down, almost imperceptibly, under the influence of tidal friction. The Moon is also receding from Earth. It is slowly moving away at a rate of roughly 3.8 centimeters per year. That is about the speed at which fingernails grow, which makes the Moon's escape feel oddly personal and slightly rude. This measurement comes from lunar laser ranging experiments. During the Apollo missions, astronauts placed retroreflectors on the Moon's surface. A retroreflector is a special mirror-like device that sends light back toward its source. Scientists on Earth fire laser pulses at these reflectors and measure how long the light takes to return. Because light travels at a known speed, the round-trip time reveals the distance to the Moon with extraordinary precision. NASA, the Apollo missions and lunar laser ranging observatories have all played important roles in measuring this distance over time. These measurements confirm that the Earth-Moon system is not fixed. The Moon is still drifting outward, and Earth is still very gradually losing rotational speed. The energy involved does not simply vanish. Some of it is dissipated as heat through tidal friction. Ocean tides rubbing against seafloors and coastlines, water moving through shallow seas, and Earth's body flexing under gravitational stress all convert some mechanical energy into thermal energy. It is not enough to make the ocean noticeably warm from one tide to the next, but physically, the energy is being degraded into heat, as the laws of thermodynamics require. This means the tide is not only a motion, it is a long-term exchange between Earth's spin and the Moon's orbit. Every tide is part of a vast gravitational negotiation that has been going on since the Moon formed. The Moon raises tides. Earth's rotation carries those tides forward. Gravity tugs between the offset bulge and the Moon. Earth slows. The Moon recedes. On the scale of a human evening, nothing seems to change. The Moon rises, the sea moves, and the day remains comfortably familiar. But over deep time, the Moon has been altering the length of Earth's day, shifting outward and reshaping the planet's rhythm. It does not only control the ocean now. Through tides, it has been quietly touching Earth's rotation since ancient seas first moved beneath its pull. The ocean is not the only part of Earth that responds to the Moon. That may sound strange at first because tides are usually imagined as something watery. The sea rises, the sea falls, and the rocky ground seems steady beneath your feet. A cliff does not appear to swell. A pavement does not visibly breathe. A mountain does not politely lift itself and settle back down again under moonlight, which is probably for the best because hiking would become much more confusing. But Earth itself has tides. These are called solid Earth tides. They happen because the moon and the sun do not only pull on seawater, they pull on the entire planet. The rocky body of Earth is slightly deformed by lunar and solar tidal forces, just as the oceans are. The difference is that rock is far less mobile than water, so the effect is much less obvious. The ocean can flow, pile up, rush through channels and spread across mudflats. The solid Earth responds more quietly by flexing. Earth is not perfectly rigid. Over short timescales, rock feels solid and unyielding, but on a planetary scale it has a small amount of elasticity. Elasticity means a material can deform under stress and then partly return toward its original shape. The Moon's uneven gravitational pull stretches Earth very slightly along the Earth-Moon line. The Sun adds its own smaller tidal contribution. Together they cause the crust beneath our feet to rise and fall by small but measurable amounts. In some places, solid Earth tides can lift the ground by several tens of centimetres. That is tiny compared with the size of Earth, but it is not nothing. It is enough to matter for precise scientific measurements. The ground may seem still to human senses, but sensitive instruments can detect its movement. Earth is quietly flexing all the time, not like a soft rubber ball, but like a huge rocky planet responding to gravity with the smallest possible stretch. This matters for geodesy, the science of measuring Earth's shape, gravity field, orientation, and movement. Precise geodesy has to account for solid Earth tides because they slightly change the position of points on Earth's surface. Satellite navigation systems also depend on accurate models of Earth's shape and motion. When measurements are being made to centimetre-level precision, a ground movement of several centimetres is no longer something that can be politely ignored. Gravimeters, which measure tiny changes in gravitational acceleration, also detect tidal effects. As Earth flexes, and as the Moon and Sun change position overhead, the local gravitational field changes slightly. Observatories that study Earth rotation, crustal motion, seismic behaviour, and reference frames must include these subtle tidal motions in their calculations. Scientific organisations such as the International Earth Rotation and Reference Systems Service help maintain the reference systems used to track Earth's orientation and motion with high precision, while geophysical research institutions around the world study how the planet responds to forces from space. There is another effect as well: ocean loading. As ocean tides move water around the planet, they shift enormous amounts of mass. When high tide piles more water over a coastal shelf or ocean basin, that water has weight. The crust beneath and around it can bend slightly under the load. When the tide falls and the water moves away, the load changes again. This means ocean tides do not only move across the crust, they also press on it, flex it, and alter the local shape of the ground by small amounts. Ocean loading is especially important near coastlines and shallow seas, where large tidal ranges can move great volumes of water in and out. The Bay of Fundy, the North Sea, and other strongly tidal regions are not just places where the water level changes dramatically. They're also places where the shifting weight of seawater can subtly affect the solid Earth nearby. The effect is small, but modern instruments are sensitive enough to notice it. This gives tides a deeper meaning. The Moon is not merely tugging at a thin surface layer of water. It is acting on the whole planet. The oceans show the effect most visibly because water moves easily. Rock hides the effect because it is stiff, heavy, and extremely committed to looking dependable. But beneath that dependable appearance, Earth is still responding. The crust rises slightly, falls slightly, bends under ocean loading, and shifts in ways that careful instruments can measure. So the moon's control reaches beyond the ocean, even though the ocean makes that influence easiest to see. The tide at a beach is the most dramatic everyday sign of lunar gravity, but it is not the only sign. The sea moves, the solid planet flexes, the weight of the water presses into the crust, the sun adds its smaller share, and the whole Earth, not just the shoreline, participates in the quiet gravitational rhythm. The moon controls the ocean because the ocean can answer visibly. But the deeper truth is that Earth itself is part of the tide. Predicting the tide begins with a simple observation that becomes surprisingly sophisticated. The sea repeats itself, but not perfectly. At a harbour, the water rises and falls each day. The pattern is connected to the moon, the sun, and Earth's rotation, but it is also shaped by the particular coastline, the depth of the seafloor, the width of channels, the shape of bays, weather, conditions, and long-term records of how the water has behaved before. A tide table may look calm and tidy, with times and heights neatly printed beside the name of a port, but behind those numbers is a careful combination of astronomy, mathematics, measurement, and local memory. The astronomical part is the oldest and most predictable. The positions of the moon and sun can be calculated very accurately. Scientists know when the moon will be new, full, near first quarter, or near last quarter. They know when lunar and solar tidal forces will reinforce each other to produce spring tides, and when they will partially oppose each other to produce neap tides. They can calculate the changing distance of the moon, the tilt of the moon's orbit, the position of the sun, and the rotation of Earth. Celestial mechanics gives the tide its broad schedule. But astronomy alone is not enough. The same moon can produce very different tides at different coastlines. A harbour inside a narrow estuary does not respond like an open ocean island. A shallow bay does not behave like a deep continental margin. The Bay of Fundy, the Severn Estuary, the North Sea, the English Channel, and a small Mediterranean harbour all receive the same astronomical forcing, but the local result can be completely different. So scientists also need measurements from the sea itself. One important method is harmonic analysis. This is a mathematical technique that breaks the tide into repeating components. Each component is linked to a particular astronomical rhythm involving the moon, the sun, and Earth's motion. Instead of treating the tide as one simple rise and fall, harmonic analysis treats it as a combination of many repeating influences layered together. Some components follow the moon's daily rhythm. Others follow the sun's daily effect. Some are connected to the moon's monthly cycle, or to longer changes in lunar orbit. Add them together correctly, and the complicated tide at a particular location can be predicted with impressive accuracy. This approach became especially powerful in the 19th century. Lord Kelvin, whose name was William Thomson, helped develop mechanical tide prediction machines that used gears, pulleys, and rotating parts to combine tidal components and draw predicted tidal curves. These machines were remarkable pieces of engineering. Before electronic computers, they could calculate future tides by mechanically adding together the rhythms found through harmonic analysis. It was celestial mechanics translated into brass, wire, wheels, and patience. Modern tide prediction now uses digital computers rather than great mechanical machines, but the basic idea remains connected to the same principle. Find the repeating patterns, understand the local response, and combine them carefully. Tide gauges measure sea level at fixed coastal locations, building long records of how the water rises and falls. Satellite altimetry measures sea surface height from orbit, helping scientists map large-scale ocean behaviour. Bathymetric data, which describes the shape and depth of the seafloor, allows models to simulate how tidal waves move through real ocean basins. Long-term observations reveal local quirks that pure theory might miss. Organisations such as the National Oceanic and Atmospheric Administration, the UK Hydrographic Office, and the Permanent Service for Mean Sea Level help collect, manage, analyse and distribute tide and sea level information. Their work supports tide tables, nautical charts, sea level records, coastal planning, and scientific research. The information may seem ordinary when seen as a number beside high tide, but it represents a vast practical bridge between sky and shore. Accurate tide prediction matters because tides affect so much human activity. Shipping depends on safe water depth in ports, channels, and harbours. Fishing crews need to understand tidal currents and access to grounds. Coastal engineers design sea walls, bridges, docks, and flood defences with tidal behaviour in mind. Flood risk changes when high tides combine with storm surge, strong winds, and low atmospheric pressure. Tidal renewable energy projects depend on knowing when and where water will flow fastest. Even ordinary beach safety relies on tide prediction, because a pleasant walk on exposed sand can become less pleasant when the sea quietly returns behind you. Still, prediction is not the same as perfect control. Tide tables can forecast the astronomical tide very well, but weather can alter the actual water level. Strong winds can push water toward or away from shore. Low atmospheric pressure can let the sea surface rise slightly. Storm surge can add dangerous extra height. Rivers can flood into estuaries. So real-world coastal forecasting often combines tide prediction with meteorology and ocean modelling. This is what makes the science so elegant. The moon's pull becomes a measurable rhythm. That rhythm becomes data. Data becomes models. Models become tide tables, navigation guidance, flood warnings, and safer coastlines. What began as people watching the waterline on rocks has become a global scientific system using satellites, observatories, mathematics, and centuries of accumulated coastal knowledge. The tide is still the same old motion, the ocean rising and falling under the influence of the moon, the sun, and a rotating earth. But now that motion can be measured, separated into rhythms, modelled and used, the sea keeps its ancient schedule, and science has learned how to read it. The tide is usually calm enough to feel predictable. It rises, it falls, it returns, and in most places it does this with the quiet reliability of a clock made of seawater. But when a storm arrives, that familiar rhythm can become part of something far more serious. Coastal flooding often happens when several forces overlap. The astronomical tide may already be high. A storm may push water toward the coast. Strong winds may pile the sea against land. Large waves may break over beaches, seawalls, dunes, and cliffs. Low atmospheric pressure may allow the ocean surface to rise slightly. Rivers may be swollen by heavy rain, trying to drain into an estuary just as the sea is pushing inland. None of these effects needs to act alone. The danger often comes from their combination. One of the most important storm-related effects is storm surge. A storm surge is a rise in sea level caused mainly by strong winds pushing water toward the coast and by low atmospheric pressure associated with a storm system. Wind is often the main driver. As powerful winds blow over the sea, they drag the surface water along with them. If that moving water is pushed into a coastline, a shallow shelf, a bay, or an estuary, it can pile up. Low atmospheric pressure adds to the effect because air pressing less strongly on the ocean surface allows the water to rise a little, like a very large and deeply unhelpful version of letting a cushion puff upward. Storm surge is separate from the normal astronomical tide, but it can interact with it. The tide is produced by the gravitational influence of the moon and the sun, shaped by Earth's rotation and local geography. Storm surge is produced by weather, but at the coast people experience the total water level. The sea does not arrive politely labelled in separate layers saying, this part is tide and this part is storm surge. It simply rises. This is why timing matters so much. A storm that arrives near low tide may still be dangerous, but the water has more vertical room before it reaches roads, homes, ports, seawalls, and flood defences. The same storm arriving near high tide can produce much worse flooding because the ocean is already elevated by the astronomical tide before the surge is added. A spring tide, when the tidal range is especially large, can make this worse still if it coincides with strong winds, low pressure, and large waves. Waves add another layer. Storm waves can carry water higher up beaches and against structures, especially when the background sea level is already raised by tide and surge. This process, often called wave run-up, can overtop defences, erode dunes, damage seawalls, and flood low-lying areas. In estuaries, high tides and storm surge can also slow river drainage, meaning rainwater from inland areas may struggle to escape into the sea. The coastline becomes a meeting point of sky, river, wind, ocean and moon, which is scientifically fascinating and, from a planning perspective, mildly terrifying. Sea level rise now changes the baseline on which all of this happens. As global mean sea level rises, a high tide begins from a higher starting point. A storm surge of the same height can reach farther inland than it would have in the past. Flood levels that were once rare can become more frequent because the ordinary sea surface has shifted upward. Scientific bodies such as the Intergovernmental Panel on Climate Change have assessed sea level rise as a major long-term risk for coastal regions, while national meteorological agencies, oceanographic agencies, and flood forecasting services use tide, surge, weather, and wave models to warn communities when dangerous conditions may develop. It is important to be clear about what the moon does and does not do. The moon does not cause storms. It does not create global sea level rise. It does not decide that a coastline has had too peaceful a week and could use some drama. Storms are driven by atmospheric conditions, heat, pressure differences, wind patterns, and weather systems. Sea level rise is linked mainly to the warming of ocean water and the melting of land ice, along with regional land movement and ocean circulation changes. The moon's role is different. It sets part of the tidal timing and contributes to the height of the astronomical tide. That timing can strongly affect how severe a coastal flood becomes. Understanding tides is therefore not only beautiful science, it is practical. It matters for flood barriers, harbour design, coastal roads, emergency planning, evacuation warnings, shipping schedules, fishing communities, offshore energy, and the safety of people walking on beaches or living near estuaries. A tide table is not just a list of times. In the right conditions, it is part of a safety system. The moon's pull remains quiet, regular, and distant. But when its rhythm meets a storm-driven sea, the result can be powerful. The same tide that gently lifts boats in a harbour can become part of a dangerous total water level when wind, pressure, waves, rivers, and rising seas combine. To understand the tide is to understand one of the ways Earth connects the sky above, the ocean below, and the vulnerable edges where people have so often chosen to live. The moon controls the ocean in a way that is both real and indirect. It does not command the sea like a hand moving water from one side of the planet to the other. It does not drag a single neat wave around Earth. It does not simply lift the ocean beneath itself and then let it drop again. The truth is quieter, more subtle, and more beautiful. The moon controls the ocean through tidal forces, and tidal forces are created because the moon's gravity does not pull on every part of Earth equally. The side of Earth facing the moon is a little closer, so it feels a slightly stronger lunar pull. Earth's centre feels a slightly weaker pull than that near side. The far side feels weaker still. Across the width of the planet, this difference creates a stretching effect. That stretching is the beginning of the tide. It is not the moon overpowering Earth's gravity, because Earth's gravity still holds the ocean firmly to the planet. It is the moon adding a small uneven influence across a huge world, and over the scale of entire oceans, small differences become powerful. From that uneven pull come the broad tidal bulges often shown in simple diagrams, one on the side facing the moon and one on the far side. Those diagrams are useful, but they are only the opening sketch. Earth is rotating beneath the tidal pattern. The moon is moving in its orbit. The sun adds its own tidal influence. Around new moon and full moon, lunar and solar tides reinforce each other, producing spring tides with larger tidal ranges. Around the quarter phases, the sun and moon pull at roughly right angles, producing neap tides with smaller ranges. Already the ocean is following more than one rhythm. There is the daily rhythm of Earth turning through tidal regions. There is the lunar rhythm of the moon's orbit, which gives the tide its slightly delayed timing from day to day. There is the monthly rhythm of spring and neap tides, written into the changing alignment of the sun, earth, and moon. The ocean is not simply rising and falling, it is responding to a moving celestial arrangement. Then Earth itself makes the story more complicated. Continents block the water. Ocean basins have different shapes and depths. Continental shelves slow incoming tidal waves. Narrow bays can funnel water into smaller spaces. Estuaries can amplify the tide until it becomes a rushing bore. In the Bay of Fundy, the shape and natural resonance of the bay help produce some of the largest tidal ranges on Earth. In the Severn Estuary, narrowing channels and shallow water help create dramatic tidal movement. In other places, the tide remains small because the basin shape and local dynamics reduce the ocean's response. Real tides are dynamic. They rotate around amphidromic points. They are bent by the Coriolis effect, which arises from Earth's rotation. They are delayed by inertia, reshaped by friction, and altered by coastline geometry. They move horizontally as tidal currents, rushing through places such as the English Channel, the Pentland Firth, and the Strait of Messina. They stir the deep ocean through internal tides, where tidal energy travels along density boundaries shaped by temperature and salinity. They move sediment, build mudflats, feed salt marshes, shape estuaries, and create habitats that life has learned to follow. So the moon's control is not simple control. It is not direct management. The moon is not hovering above the sea with a clipboard, making sure every harbour receives the correct amount of water at the correct time, although tide tables do sometimes make the arrangement look suspiciously organised. Instead, the moon sets the main gravitational pulse. Earth turns that pulse into motion. The sun changes its strength. The continents interrupt it. The seafloor reshapes it. Local coastlines translate it into the tide that actually appears at the shore. The relationship also reaches beyond a single day. Tidal friction slowly transfers angular momentum from Earth's rotation to the moon's orbit. Earth's spin is gradually slowing. The length of the day has increased over geological time. The moon is slowly moving away from Earth at roughly the pace fingernails grow, measured through lunar laser ranging using retroreflectors left by Apollo astronauts. The same tidal relationship that lifts the sea today has been changing the Earth-Moon system across billions of years, and still, from the shore, all of this can look wonderfully simple. The moon rises, the water climbs, wet sand darkens under the returning sea, a harbour fills, a rock pool disappears. The ocean comes quietly forward under silver light, not because of magic, but because of celestial mechanics, gravity, distance, rotation, orbit, friction, resonance, and the shape of Earth itself. Every tide is local, but no tide is only local. Each one is a small expression of a planetary relationship. The water at one beach is answering the same moon that pulls on the whole Earth, the same sun that modifies the rhythm, the same rotation that carries coastlines through the pattern, and the same ocean basins that turn invisible gravity into visible motion. The sea rises beneath the moon because Earth is part of a larger dance, and at the edge of the water, that dance becomes something quiet enough to watch. The moon controls the ocean because its gravity creates tidal forces, and those tidal forces stretch Earth's oceans into rhythmic patterns as the planet rotates. That is the calm answer at the heart of the title. The moon does not control the sea by pulling it upward in one simple place, like a hand lifting water from a bowl. It does not drag a single wave around the planet. It does not command every harbour, beach, estuary, and mudflat directly. Instead, it creates an uneven gravitational pull across Earth. The side of Earth facing the moon is pulled slightly more strongly. Earth's centre is pulled a little less strongly. The far side is pulled less strongly again. That difference is small, but across the width of an entire planet it matters. From that uneven pull comes tidal force, the stretching effect that helps shape the ocean into patterns of higher and lower water. Earth then rotates through those patterns, carrying coastlines into and out of high tide and low tide. The sea rises, pauses, falls, and returns, not because the moon is physically lifting the ocean like a blanket from one edge, but because gravity changes subtly from one side of Earth to the other. Long before this could be explained with physics, people already knew the sea had a schedule. Coastal communities watched the tide for fishing, shell gathering, navigation, harbour travel, and survival. They noticed that the water's rise and fall often seem connected to the moon. Around the North Sea, the Atlantic coast, the Mediterranean, and across the great ocean routes of Polynesian navigators, tide knowledge was practical knowledge. It was learned from rocks, mudflats, boats, channels, and sometimes from the immediate disappointment of being caught by water that had returned exactly when it said it would, if only someone had been paying attention. Ancient thinkers tried to explain these patterns too. Aristotle and other Greek philosophers looked for order in nature, even though they didn't yet have the concept of universal gravitation. Later, Galileo Galilei offered a tidal explanation connected to Earth's motion, but he did not correctly identify the moon's gravitational role. His idea was wrong, but it still mattered, because it showed tides being treated as a physical problem linked to planetary motion. The sea was no longer just mysterious behaviour at the shore, it was part of the moving heavens. Then Isaac Newton gave science the central key. His theory of universal gravitation showed that the same force pulling objects toward Earth also connects Earth, the moon, the sun, and the planets. Gravity acts between masses, and its strength depends on mass and distance. With Newton's insight, the moon's influence on the ocean became something that could be understood as part of the same physical order that keeps the moon in orbit. That explanation also clarified why there are two tidal bulges in the simplest picture, not one. The near-side bulge forms because the ocean facing the moon feels a slightly stronger pull than Earth's centre. The far side bulge appears because Earth's centre is pulled slightly more strongly than the far side ocean. The result is a stretching pattern along the Earth-Moon line. The far side tide is not caused by a mysterious outward force throwing water away. It is part of the same geometry of uneven gravitational acceleration. But the simple two-bulge diagram is only the beginning. Earth rotates, and the moon moves in its orbit, so the tidal rhythm follows the lunar day, a little longer than an ordinary solar day. This is why tides usually arrive later each day. Many coastlines experience 2 high tides and 2 low tides in a little over one day, but not all of them. Some places have one main high tide and one main low tide. Others have mixed tides, with uneven highs and lows. The moon sets the rhythm, but the real ocean plays it differently from place to place. The sun also has a role. Its gravity is far stronger overall, but because it is much farther away, its tidal force on Earth is weaker than the moon's. Still, solar tides combine with lunar tides. Near new moon and full moon, the sun, moon and Earth are roughly aligned, and their tidal effects reinforce each other, creating spring tides with larger tidal ranges. Near first quarter and last quarter moon, the sun and moon pull at roughly right angles, producing neap tides with smaller ranges. The moon's phases do not change its gravity, but they reveal the changing alignment that alters tide strength. Pierre-Simon Laplace helped move tide theory beyond simple static bulges by treating tides as dynamic ocean waves shaped by rotation, depth, and basin geometry. That was essential, because real tides are far messier than textbook diagrams. Continents interrupt the water. Ocean basins have different sizes and depths. Continental shelves slow tidal waves. Bays and estuaries can amplify them. The Bay of Fundy can produce enormous tidal ranges because of its funnel shape and resonance. The Severn Estuary can generate dramatic tidal movement and tidal bore conditions because of its narrowing, shallow form. Elsewhere, tides are modest, because the basin shape and local dynamics weaken the ocean's response. In many ocean basins, tides even rotate around amphidromic points, where the tidal range is very small. These amphidromic systems form because tidal waves move through rotating basins, influenced by the Coriolis effect, seafloor shape, and coastline geometry. So the tide is not just water going in and out, it is a broad, rotating, delayed, reshaped motion spread across entire seas. Tides also move horizontally as tidal currents. Flood tide carries water in. Ebb tide carries water out. In places such as the English Channel, the Pentland Firth, and the Strait of Messina, tidal currents can move enormous volumes of seawater through narrow passages. These currents matter for navigation, sediment transport, marine habitats, and coastal safety. Below the surface, the moon's influence reaches even deeper. Internal tides move along density boundaries inside the ocean, where layers of different temperature and salinity meet. As tidal currents pass over underwater ridges, continental slopes, and seamounts, they can generate internal waves that travel through the deep sea. These hidden motions help mix heat, nutrients, oxygen, and dissolve substances, linking tides to ocean circulation and climate systems. Life has learned these rhythms too. Barnacles, mussels, limpets, crabs, sea anemones, rockpool fish, shorebirds, marsh plants, mangroves, and countless microorganisms live in worlds shaped by flooding and draining. Some organisms have circadian rhythms, internal biological timing linked to the tide. The moon does not consciously direct life, but its gravitational rhythm creates environmental patterns that natural selection can respond to. Across deep time, tides have also changed Earth itself. Tidal friction dissipates energy as heat, slows Earth's rotation, and transfers angular momentum to the moon's orbit. The day has lengthened over geological time, and the moon is slowly moving away from Earth. Lunar laser ranging experiments using Apollo retroreflectors have measured that gradual recession with remarkable precision. Modern tide prediction brings all of this into practical use. Tide gauges, satellite altimetry, bathymetric data, harmonic analysis, computer models, and long observational records allow organisations such as the National Oceanic and Atmospheric Administration, the UK Hydrographic Office, and the Permanent Service for Mean Sea Level to predict the sea's movement with great care. What began as watching the waterline on rocks has become astronomy, mathematics, oceanography, and coastal planning working together. So tides are not the same everywhere because Earth is not the same everywhere. The same lunar force can be magnified, delayed, rotated, weakened, or redirected by local geography. The Moon provides the main gravitational rhythm, but Earth's oceans, continents, seafloor, coastlines, the Sun's additional gravity, and the motion of the planet itself decide how that rhythm appears, and that is what makes tides one of the clearest everyday examples of celestial mechanics. A body in space produces visible change on Earth. The Moon hangs above a dark coastline, quiet and distant, while the ocean moves beneath it in an ancient rhythm. The water rises, the shore disappears, the tide turns, and in that slow breathing of the sea, there is a reminder that the ocean is never entirely separate from the sky.